Okay, so now what we're going to do is we're going to learn how to do two things. First, how to tell if a molecule is polar or not, and then how to use that information to figure out what kind of attraction is in between the molecules. So let's start off first with just the molecule itself. So we have four basic shapes. We have linear, and I'm going to use nitrogen as an example. We have tetrahedral, and I'm going to use methane as an example. We have bent, and I'm going to use water as an example. And let's use aluminum trichloride. For pyramidal. Okay? Now, if we look at these four molecules, they all look very, very different. Now, what you've learned so far is if I ask you, A, how to draw it, you guys know how to do this. You know how to take a formula and make it into a drawing. Second, if I ask you what kind of bonds, you know to look at the elements and say, okay, those bonds are between the nitrogens are going to be nonpolar because they're bonded to themselves, whereas the bonds with these next three are all going to be polar because the bond is between two different elements. What we have to do when we look at the polarity of the molecule is we have to know what's called the partial charges. Now, none of these are ionic, which means that the electrons are not being transferred, so we don't have ions. But what we do have is an imbalance. If you look at nitrogen, if I draw it with electrons, and I'm going to use X's in black for that nitrogen, and then for this nitrogen I'm going to use green dots. This nitrogen is happy with 8 electrons because it's sharing all 6 in the middle. This nitrogen is also happy with 8 because it's sharing the same 6. Now, since it's nitrogen bonded to itself, nitrogen bonded to another nitrogen, these electrons are right in the middle because the electronegativities are exactly the same. That's why this is a nonpolar bond. Since that's the case, we can look at this. We can take a step back and look at this as a molecule and say, okay, is this balanced as far as the charges are concerned? And the answer is yes. So what we would call this is a nonpolar molecule. Okay? Now look at methane. We're going to skip water for now. Look at methane. Now, methane is tetrahedral. It's tetrahedral in shape. The bond between carbon and hydrogen is going to be a polar bond. Why? Because it's two different elements. Since it's two different elements, it has two different electronegativities. So, when you look at this, you're going to have carbon, and I'm going to use X's for carbon. And then you're going to have hydrogen. And I'm going to use the circle for hydrogen. But the hydrogen remember, all you need is 2. So all 4 of these hydrogens are happy, and this carbon is happy with the 8 in the middle. Now, if you look at that drawing, you'll notice that the electron for hydrogen is not in the middle anymore, not like it is with nitrogen. Okay, if you look at the drawing, the electron is much closer to the carbon than it is to the hydrogen. And the reason for that is that carbon has a higher electronegativity. You can tell that by looking at the periodic table. It tells you. And look at the chart that I gave you last week. So carbon has a higher electronegativity. Therefore, when they share these electrons, that bond is going to be polar, which by definition means that the electrons are closer to one element than the other. How do you decide which one is closer to? Well, it's which one has the higher electronegativity, which is carbon. Now, why is that important now is this. Since the electrons are closer to the carbon is going to become more negative. So we have what's called a partially negative area around the carbon. Now you see that symbol I just wrote? I'm going to write it really big. It looks like this. Okay? Looks like a fancy S. It's a Greek symbol. I'm not doing it totally correct, but that's as close as we're going to get. Okay? That means partial. That's different from being an ion. An ion is when you totally transfer the electrons, so it's a positively charged ion. This is not an ion. This is just an atom where the electrons are closer to it, so it's more negative. Since the electrons are being pulled away from the hydrogen is going to now become partially positive. Because remember, electrons are negatively charged particles. Now, if you step back and look at that, okay, even though the bonds between C and H are polar, when you step back and look at the molecule as a whole, the positives and negatives are equally balanced. Okay? In other words, is it symmetrical? Can you take this molecule like it was a piece of paper and fold it in half, both left and right and up and down, and have it match? And the answer is yes. So this is, again, a non-polar molecule. So the question I want to make sure we know the answer to, does it have to have non-polar bonds to be a non-polar molecule? And the answer is absolutely not. That actually has nothing to do with it. The type of bond has nothing to do with the type of molecule. Okay, the type of bond is decided by whether or not you have equal electronegativities. The type of molecule is decided by whether or not the molecule as a whole is equally distributed or symmetrical. For example, again, look down at AlCl3. AlCl3 is trigonal planar, which means that it is going in three different directions, all on the same plane, like on a piece of paper. Chlorine is going to have a much higher electronegativity than aluminum. So the electrons are going to be shared unequally more towards chlorine than aluminum because it's going to pull them more. So all these chlorines will be partially negative, while the aluminum in the middle will be partially positive because the electrons are being pulled away from it. So even though the bonds in between the aluminum and the chlorine are very polar, if you step back and look at the molecule as a whole, is this equally distributed? And the answer is yes. So again, this is a non-polar molecule. Okay? So you have three examples. Okay, there's three shapes that are going to be traditionally symmetrical and therefore traditionally nonpolar. And that is linear, tetrahedral, and trigonal planar. Those three are usually nonpolar. The difference would be is, let's say instead of CH4, I had C with three H's and I threw a fluorine over there or something like that. That would make it completely off balance and wacky, but that's really unusual, okay? Now, if you look at these three, okay, we want to now talk about intermolecular forces. An intermolecular force, let's write this down. An intermolecular force is the attraction in between molecules. From here on out, I'm not going to say intermolecular force because it's a lot of words. I'm just going to say IMF, intermolecular force. This is the attraction in between molecules. For example, if I take nitrogen and put it next to another nitrogen, do you think that there would be an attraction between these two molecules? Now, one thing that you should remember from what we've talked about many, many times in the past is that for there to be an attraction, there absolutely has to be positive and negative sides, because that's what attracts, positives and negatives. Now, what we just talked about is the fact that this is a nonpolar molecule and therefore doesn't have positive and negative sides. So is there an attraction? Immediately you should say no, okay? Which should make sense, because what does nitrogen normally exist as? It exists as a gas. Gases, if you remember, are molecules that are far apart. And the reason they're far apart is because they don't really have any attraction for each other at all. However, they do have one small, weak kind of attraction called London dispersion. Now, London dispersion forces are the result of the fact that molecules are flipping and spinning through space, and therefore they're wobbly. And when something is wobbly, it gets out of balance for small amounts of time. You got to remember that nitrogen, even though we're talking about just the valence electrons when we draw these structures, has 14 electrons total. Okay? Right now, only 6 of them are involved in bonding, but we have 28 total electrons between these two nitrogens. So all of these electrons are involved in these clouds that we talked about before in the other video, and as nitrogen is flipping and spinning through space, these electrons don't stay in one spot, they wobble. In your mind's eye, picture a water balloon. You know, if I filled a water balloon up and just held it in my hand, it'd be perfectly round. But if I took it and then whipped it across the room, and we were able to slow motion video the water balloon as it flew through the air, you can imagine that the water inside the balloon is going to slosh around. And as it sloshes around, it's going to change the shape. And there's going to be small instantaneous moments where there's more water on one side of the balloon than the other. The same thing happens with molecules. So when they're flipping and spinning through space, when all those electrons are momentarily more on one side than the other, then we have a small moment where there's a little bit of negative and a little bit of positive. But it goes away really fast. But since it's there for a little bit, we do have a little bit of an attraction. It's very, very weak, but it's there. London dispersion. So, if you have identified a molecule as symmetrical and therefore nonpolar, the intermolecular force in between nonpolar molecules is going to be London dispersion. Okay? Now, what if the molecule is polar? In other words, what if it's not symmetrical? The best example is water. As we talked about, water looks like this. Here's hydrogen. Now, for the same reasons we talked about with methane, the electrons that are being shared between the oxygen and the hydrogen are not going to be shared equally. Oxygen has a much higher electronegativity than hydrogen, so it's going to pull that pair closer to it. So the hydrogens in water are going to become partially positive, whereas oxygen is going to become partially negative. So if you take a step back and I ask you what kind of molecule is water, now you're going to ask yourself, are the charges around the central atom equally distributed? And the answer is absolutely not. You have a bunch of positives on this side, but you don't have any positives on this side at all. Okay? Again, can you take this molecule and fold it in two directions and match up? And the answer is no. So the main question you want to ask yourself, is it symmetrical? And the answer is no. Since it's not symmetrical, this is a polar molecule, which by definition has a positive side and a negative side. So we have another name for polar molecules. They're also called a dipole. Di meaning two, pole meaning a positive and negative side. Now, polar molecules, now it should make sense to you. If we put a polar molecule next to another polar molecule, will they have an attraction for each other? And the answer is yeah, because positive attract negatives. So if I take a water molecule and put it next to another water molecule, and remember that the oxygens are partially negative and the hydrogens are partially positive, it should make sense to you that the positive side of the hydrogen of the water molecule is going to be stuck to the negative side of the other one. And if we draw yet another one, and remember, if we have a bucket of water, we got cajillions of these, right? Then that's going to be attracted to that. Okay, positives attract to negatives. It should make sense, and this is the nice part of this, is that the name of this is really easy. Okay, the intermolecular force, which is the attraction in between dipole molecules, is called dipole-dipole. Easy, right? Dipole-dipole. So if I ask you what kind of bonds are in water, you're going to say polar right away, because it's two different elements. If I ask you what kind of molecule water is, you're going to say it's a polar molecule. You're going to say it's a polar molecule because it's not symmetrical. The charges around the oxygen are not balanced. So I'm going to ask you the third question, which is what kind of attractions, therefore, are in between water molecules, and you're going to say dipole-dipole. Now, I'm going to add one more wrinkle to this. If the molecule has hydrogen bonded to nitrogen, oxygen, or fluorine, okay? If the molecule has hydrogen bonded to any of those three elements, we're going to take it one step further, and we're going to call it a hydrogen bond, which is a very strong type of dipole-dipole. A very strong type of dipole-dipole. It's not a different type of dipole-dipole. Okay, it's just strong. Like if I say, this is a girl and this is a boy, those are both types of humans. They're not different kinds of organisms. They're both humans, but they're just different. Now, a dipole-dipole, remember, is when you have a molecule attracted to another molecule a lot. Okay, now water. If you look at water, does water have dipole-dipole? Yes, because it's a dipole attracted to another dipole. Is it also then a hydrogen bond? So you look at the molecule, does it have hydrogen? Yes. Is that hydrogen attached directly to N, O, or F? And it's attached to an O. So we can label this as hydrogen bonding as well. Okay? So, I'm going to start the next video with a summary chart that will take us through how to figure out if it's symmetrical and therefore polar or nonpolar, and then how to figure out therefore which IMF. And then after we do that, that summary chart, we're then going to do the notes. We're going to do the homework together. Okay?